Okay, so in the last video we defined some maps zeta I from delta k plus 1 to 0, 1 cross delta k. And we proved various things about them. That's what we'll recall in a minute. But now we're going to put zeta hat k is the sum. So this was defined, it's only from I running from 0 to k. So here we can put take a sum from I from 0 to k. And we're going to put in a sign -1 to the power I multiplied by this zeta I. Okay, so this is this delta. This is a element of ck of this is an element of ck plus 1 of this product, and so this, when we take this alternating sum of terms here, this is still an element of ck plus 1 of this product 0, 1 cross delta k. And we want to know about what's the boundary of this. Okay, so we just recall the general procedure for taking the boundary. Well, again, we've still got the sum from I is 0 to k, and then the boundary involves a sum from j, because this is in k plus 1. Now this is a sum from j is 0 to k plus 1. And then you get a -1 to the j combined with that -1 to the I there. So it's a -1 to the power I plus j. Zeta I composed with delta j. Okay, and now this is an element of ck of 0, 1 cross delta k. Okay, so let's also consider we've got this zeta hat k minus 1, so that's going to be a k chain in 0, 1 cross delta k minus 1. And therefore, we can apply push it forward using 1 cross delta j, say, of zeta k minus 1 hat. Okay, so this delta j was a map from delta k minus 1 into delta k. So this is also an element now in ck of 0, 1 cross delta k. And we also had the top and the bottom maps from the delta k to 0, 1 cross delta k. And therefore, we can these are maps from the k-simplex into this space, so they're singular k-simplices. We can regard these also as elements of the same chain group. So the key claim that we need to make is that if we take the boundary of the zeta hat k, and then we're going to add in this bunch of terms like this. This is going to be the yeah. So this was a remember, this was a delta j mapping into capital delta k. That's valid for j is 0 all the way up to k. Yep, so we take all possible terms of this type here and multiply them by appropriate signs and add them up. I'm going to add that onto there, and then I want to claim that this is equal to the top minus the bottom. Okay, so we've got this sum here. Let's call this one A. Maybe. And this thing here, let's call this B. Okay. Okay. So what can we say about this? So So in A, well, the case I is j is 0. that gives us zeta naught delta naught, and by what we said in the last video, that's just equal to the top. Whereas if we do the last case here, we do I is k, j is k plus 1. So what's the plus or minus sign? So here you've got I plus j. That's 2k plus 1, which is odd, so that's a minus sign. You get minus zeta k delta k plus 1, which is minus the bottom. And then the yeah. So then we had the yeah. So we had the got these terms zeta I, delta I, and zeta I minus 1, delta I. Yeah. So these terms have opposite sign. And they therefore cancel because these two maps are actually the same map as we proved in the last video. And so that's valid for I running from 1 up to k. Yeah, and then again from the results in the last video. So the remaining terms in A, those that are going to have j less than I or j at least I plus 2, and therefore they match up with okay. So yeah, if you look back to the results in the last video, these guys, zeta I delta j, they were either identity cross delta j composed of zeta I minus 1 or identity cross delta j minus 1 zeta I. And that's going to appear in this B here. There's zeta k minus 1 here. Zeta hat k minus 1 is the sum of all these kind of terms with the with the zeta like that, and then you're composing it with identity cross delta j. But here, this guy will appear over here with the sign minus 1 to the j plus I minus 1, whereas it appears in here with the sign minus 1 to the I plus j. Okay, and that's basically all we need to say. There's a little bit of extra bookkeeping and stuff to keep everything lined up, but I'm not going to go through it in this video. It's done a bit more carefully in the notes. But yeah, you can see that basically all the ingredients are there, all the terms are matching up, and lots of stuff is cancelling, and all we're left with is the top minus the bottom, as we've written there. Okay, so let's just write that formula again. The claim was the boundary of zeta hat k plus a sum from I is 0 up to k minus 1 to the power I of identity cross delta I pushing forward zeta hat k minus 1 is equal to the top minus the bottom. And this is in the chains, k chains of 0, 1 cross delta k. Okay, so now let's go back to topology. Okay, so So we've got two spaces x and y, and f and g from x to y are continuous. And h is going to be a homotopy between them. So remember, that means that h agrees with f on the bottom and with g on the top. Okay. So now let's suppose we've got a map u from delta k to x. So u is a basis element in the chain group ckx. So now so let me let M be this composite. So I do 0, 1 cross delta k, and then I go by the identity cross U to 0, 1 cross x, and then I go by H over to Y. And okay, so then so now this is a map from this space here into Y. So I can do M lower hash. So I'm going to put sigma of U. That's M lower hash of zeta hat k. Okay, so we had the zeta hat k. Oh yeah, so actually this was so that's in ck plus 1 of y. Okay. So this so this is a so then we can extend linearly. So this I won't just define this on the basis elements for ckx, but I just do it in the obvious way on linear combinations of those basis elements. So I get a map from ckx to ck plus 1. So remember, that's the right kind of thing to be a chain homotopy. Or a chain homotopy from c star x to c star y is a family of maps that go increased degrees by 1, with d sigma plus sigma d being whatever we want it to be. Okay, so that's what we need to check. Okay, so let's just record that definition again. Sigma of u is h composed with identity cross u applied to our zeta hat k. So that's in there. Okay. So so let's work out what's d sigma u. Okay, so then and then so this map here we were calling M. Okay, so that's d of M hash of zeta hat k. Right, but M hash, that was that was a chain map. That was we proved earlier that these chain complexes, they're functorial in your space. The induced map induced by a map topological spaces is a chain map. So this is M hash of d zeta hat k. Okay. What about sigma du? Okay. Well, that's it's going to be the sum from I is 0 to k minus 1 to the I sigma of u composed with delta I. Right? Remember that du is the sum of these terms, u composed with delta I, with the plus and minus signs, and we apply sigma to that. Sigma is a homomorphism, so we just get these sigma like here. Okay. yeah, so then we have to recall how the sigma works. So this is the sum over I minus 1 to the I. And then how do we do the sigma? You get H composed with identity cross U delta I of C to K minus 1 hat. Okay, so that's how we do that sigma. Okay. Okay. Right. So, but this this kind of H composed with identity cross U delta I, that's the same thing. Yeah, let's maybe write this kind of in a box up here. You know. So we can just break out the delta I part separately. Okay, so this is again the sum minus 1 to the I, and then and then let's maybe recall we were calling this map M, so that's M composed with identity cross delta I. So you've got here, this is just M hash of id cross delta I hash of C to hat K minus 1. Okay, and if we want, we can take out the M hash term. So M hash is a homomorphism, so I can say that's M. Can bring it out of the sum, so you get minus 1 to the J to I, identity cross delta I. Okay, so now the point is, right, I mean, this expression here was part of the identity with which we started this video. So if we add together these two terms, these two things that we've got. Okay, so that's going to be everything's involves this M hash. You've got an M hash there. You've got d zeta hat K plus this term here. Okay, but then as we you did at the beginning of this video, this expression here is the same thing as top minus bottom. Okay, so what about so we do M composed with the top. So that's M of 1 comma T, but then this thing is so that's H of 1 comma U of T. But we know that H is a homotopy, so a homotopy from F to G. So on the top, H is given by G. So this is G of U of T. So that tells me that M hash at the top is just G hash of U. And similarly, M hash at the bottom is F hash of U. So what we get here is G hash minus F hash of U. Okay. So the conclusion, so sigma is a chain homotopy from F hash to G hash. Okay, so just to restate that, So if H is a homotopy from F to G, then it gives a chain homotopy from F hash to G hash, and we proved that if you've got chain maps that are chain homotopic, then they have the same effect in homology. So you get the same maps from the homology of X to the homology of Y. And so as a corollary of that, so we can regard Hn. Well, previously we described it as a functor from top category of topological spaces in continuous maps to abelian groups. But now we see that it can be regarded as a functor from H-top. H-top, remember the morphisms of H-top are homotopy classes of maps. And if you've got two maps in the same homotopy class, they, by what we've just proved here, they give you the same map in homology groups. So we can regard this as a functor on H-top. A corollary of that, if they've got a homotopy equivalence, becomes an isomorphism in H-top. More or less the definition of what we mean by a homotopy equivalence. It's a map that becomes an isomorphism in H-top. And remember, functors send isomorphisms to isomorphisms always. So we see that you get an isomorphism of homology groups. So in particular, if X is contractible, which means it's homotopy equivalent to a point, then we know that X has got the same homology as a point. And so the homology of X, nth homology of X is going to be Z for n is 0, and otherwise it's going to be 0.